Today's material will be a bit of a whiplash for you guys, but that is not intentional. Part of the problem is that we are now getting to the point where I'm trying to build in heavier emphasis on bigger picture and overviews than go real deep into the models because we have done a lot of that. But now that you have learned a fair amount of base material, it seems to me that it's much more worth to spend some significant class time on kind of going back and taking a bigger picture approach because you need that. I mean, one of the problems with us is that we become very specialized. And once we become very specialized, our abilities go up, but then our range goes down because it is difficult to do many things. But this is where, therefore, our problem is. We need to have a big range and good depth as as experts in whatever it is that we do, be it industrial work, be it making money, be it teaching, be it doing research, be it advising some agent or client about something. So I want to start by pointing out a problem that is a very mundane problem if you look at it. For example, I tell you the only thing we have to fear and not finish the sentence. This actually happens to be a famous quote apparently from Franklin Roosevelt. Uh, the answer is the only thing that we have to fear is fear itself. That's what Roosevelt said. Now, you have plugged this in to your AI engine, and the AI engine, let's say, correctly answers this question and says, oh, it's fear itself. Now, let's step back and wonder what the AI engine might have done. The AI engine recognizes the first several words. So, the only thing we have to fear. So 1, 2, 3, 4, 5, 6, 7 words are there. Now, after the, many things could have come because you're composing a sentence. Forget about what it is. It can be, the day is going to be rainy today. It can be almost anything. You can almost start an infinite number of sentences with the. So the only is very important. But once you say the only, then the thing is belonging to a much narrower range of possibilities, right? Only what? I mean, you can't go anywhere. You have to go along more of a finite set of possibilities at this point. The only thing, okay, the only thing what? Well, the only thing that there is, the only thing that might happen, the only thing whatever. But if we give the word we, which is like an extra fresh input, then you can take off a little more, but you don't know where you're going. But once you put in fear, it's a big giveaway. So the probability of what is left over is relatively easy. If you have a good library, you're going to check if the sentence fits any known sentence and you'll blurt it out. And if you have a good library, you probably know from the library that it was spoken by Roosevelt. If you don't have a big library, if you have a more limited library, then even then, if you see fear, you probably can still construct the rest, probably with a slightly lower probability of success than what it would be if you had a bigger library. So you see, this is the reason why AI was started by physicists, because this is a Markov chain problem. It's a sequential Markov chain problem. Where a fair amount of information is given, you're guessing the remaining information. The probabilities of each of these words give you information about what is likely to come next. And this, therefore, can be a very important tool in deciphering many things, not just having fun. Another one here, not a quite such a common quote as such, I don't know, it may be, but you are smarter than, and then you don't complete. Now, you're smarter than a dog, you're smarter than a cat, you're smarter than whoever, but the sentence is supposed to get you to you are smarter than you think. Now, it is maybe more difficult than the upper one, above one, but it is not that difficult at the end of the day, because among maybe 30 possibilities or 25 possibilities or something like that, it is you are smarter than you think. So you can see this is a Markov chain problem because you are smarter than is given, but the remainder of it, you are sorting out what are the various words that you can pick. In this case, you are smarter than you, let's say, is given. Then it is quite easy because you're smarter than you. How many possibilities exist? So there is a large number of possibilities after you're smarter than, maybe let's say, for the sake of numbers, 100 possibilities. So you have, 10% chance if you're taking 10 guesses to get one right. So it has a weight that you can now imagine it has. Each possibility has a weight. Some will have more weight because the next word would be easier to guess or would make sense, and some would have less probability. For example, you are smarter than you may have, the you may have a high probability, but you are smarter than may have somewhat lesser probability. Because if you're smarter than what? I mean, there are many. You're pretty much the smartest guy in the planet. So smartest race in the planet. So you're smarter than almost any animal. That doesn't make much sense. So that kind of works to lower the probability of going along. So you see, this is the thing that these kind of chains of uh, possibilities that we are building up leads you along a likely path, not the more definitive path, but a likely path. And the likely path is going to be more and more likely the bigger and bigger your library is, and the better and better your reasoning is. So this is what AI engines do. Now, the reason why I came back to this part of the, topics we have covered is because I was quite fascinated by something, and I'll tell you what I was fascinated by. So I thought I will share it with you because this is statistical mechanics of Markov systems. And this is a page from Stanford. I don't know who did this page. It may be a student, maybe somebody else. I don't know this person, but these are called N-gram language models. I didn't know this. They're called N-gram language models. So predicting is difficult, especially about the future, as the old quip goes. But how about predicting something that seems much easier, like the next word someone is going to say? What word, for example, is likely to follow? The water of Walden Pond is so beautifully ... You might conclude that a likely word is blue or green or clear, but probably not refrigerator nor this. Refrigerator makes no sense at all. The water of Walden Pond is so beautifully this is less likely. In this chapter, we formalize this intuition by introducing N-gram language models or LMs. A language model is a machine learning model that predicts upcoming words. More formally, a language model assigns a probability to each possible next word, or equivalently, gives a probability distribution over possible next words. It's a stochastic problem that you're doing. Language models can also assign a probability to an entire sentence. Thus, an LM could tell us that the following sequence has a much higher probability of appearing in a text. All of a sudden, I noticed 3 guys standing on the sidewalk. Then that's the same set of words in a different order. On guys, all I, off, notice sidewalk 3, a sudden standing the. right? So it is this chain of reasonable probabilities that is behind a machine guessing something. How now is it being used? And that's why I thought I'd come back and cover this because I figured it's interesting. It's based upon things you have already learned, but it's not a traditional example in statistical mechanics that I could think of. So I was looking at something and I found this paper, Statistical Analysis of the Indus Script using Ngrams. So now we are talking about the Indus Valley Civilization. I don't know, Tony, if you're familiar with it. So Indus Valley Civilization is one of the rather ancient, well-developed civilization that existed in India, Pakistan, basically in the Indian subcontinent. Uh, in fact, the original sites that were found back, I don't know when, but a long time back, was a site called Mohenjo-daro, and the other site near it was a site called Harappa. So Mohenjo-daro and Harappa are two ancient cities that existed, and these cities date back to about 5,000 years ago, in that ballpark. Now, the trouble that people have had, archaeologists and others, is that they have not been able to decipher the script, the writing script that was used at the time, because it was in a language that doesn't have any known commonality with languages in use or have been in use that we know of. For example, Sanskrit, which is a mother language, has been in use in India for many, many thousands of years. We don't know how many thousands of years. Now, we don't know if these people use Sanskrit, but whatever script they use was definitely very different. And I'll show you a picture of the script. Actually, I don't have a good picture of the script somehow. I have here. So this is the kind of script. It's kind of hieroglyphic, if you will. These numbers have been assigned by these guys. And these are also I did not read this paper carefully. I didn't have time because I found it last night. But the idea is that you see these scripts, you see these texts, and then you are trying to build on that because you are trying to wonder what this means and what that means and what that means and so on, and then trying to understand what language might have been in use at the time. So you can see that there's a text, there's an incomplete text, maybe this text was missing. So they try to do a most probable restoration from scanning the corpus of the existing, uh, you know, signs, let's say, that are there, and then uh, try to come to some point as to what it might mean in what we understand now, and then try to see if it works in or not. So it's a very interesting problem. This problem was tackled by a group of people uh, who are from languages, archaeology, one theoretical physicist, which is Ranaja Adhikari, who's a professor in Cambridge, and so on and so forth. So here, the idea was to use Ngrams, the one that I just said, I talked about in the previous slide. So let's read the abstract. This paper is freely available. It's in PLOS One, which is a very good open access journal. So you can download and read it. Not that old. It's about 15, 16 years old now. The Indus script is one of the major undeciphered scripts of the ancient world. The small size of the corpus, whatever is available, the absence of bilingual texts, and the lack of definite knowledge of the underlying language has frustrated efforts at decipherment since the discovery of the remains of the Indus civilization. This was a long time ago. I mean, I read about the Indus civilization when I was in school. At the time, it was already old, and I was in school in the 60s and 70s. So you can well imagine this was done. You can look it up, but I've honestly forgotten. Building on previous statistical approaches, we apply the tools of statistical language processing, specifically n-gram Markov chains, to analyze the syntax of the Indus script. We find that unigrams follow a Zipf-Mandelbrot distribution. So it's basically a distribution of probability distribution. You can look it up online, a relatively simple one. Text beginner and ender distributions are unequal. That means beginning and end are always different, providing internal evidence for syntax. So just by looking at the patterns and the probabilities with which these patterns are coming out, by looking at the corpus of the text available, they're trying to calculate and predict how these patterns shape up. We see clear evidence of strong bigram correlations, presumably means two of these, and extract significant pairs and triplets using a long likelihood measure of association. Highly frequent pairs and triplets are not always highly significant. Let me expand this a little bit. Having trouble reading it. The model performance is evaluated using information theoretic measures and cross-validation. The model can restore doubtfully read texts with an accuracy of about 75%. We find that a quadrigram Markov chain saturates information theoretic measures using a held out corpus. So once you align 4 words, beyond that, you can't make much progress, is what it seems like they're saying. Our work forms a basis for the development of a stochastic grammar, which may be used to explore the syntax of the Indus script in greater detail. I was quite fascinated by this because this is a use of Markov chain probabilities and basic ideas of statistical analysis, combining it with known probability distributions and probabilities of how these quote unquote alphabets line up is obviously one of the current ways that I didn't know of analyzing unknown languages and see what kind of underlying grammar they might have had. And then by deeper and deeper study, try to decipher the language. Of course, deciphering of ancient lost languages is an incredibly difficult challenge. Even for Egypt, so many hundreds of years after finding the hieroglyphics, our knowledge of how to read them is very limited. There has been progress, but it's been very limited. In India, this is quite a challenge because India has so much ancient stuff, and India still has so many languages that it is a major challenge. So it tells you a little bit about how incredibly useful some of the things we are learning or we have learned is in the context of stuff that really concerns our very own existence or the languages we speak, which apparently seem so completely unrelated to statistical analysis, right? So this kind of ability to see this kind of connections between what we learn and how it can be applied or how applications have evolved over time, I think it's one of the most important learnings that we all should try to do because it's just not easy to do. We have already done this, so this is I have to go back and place those slides in when we were talking about Markov problems. We have also used, for example, this is another application that we went through, I won't repeat, random walk to study the diffusion problem, for example, to analyze the diffusion problem. First in 1D and then by extension to D dimensions, which is what we did here. So we have done this. By the way, that book by Mehan is Applied Mathematics, that's the name. And it's a Springer publication. I couldn't find the year for some reason. So I raised a lot of questions for you guys to ponder about dynamics of many body systems, linear and nonlinear effects. We touched upon this a little bit. Is this fundamental or applied science? My answer is it's both. It is really needed for us to have a deeper understanding of how nature works. Why is it not moving? Another big challenge is integrability versus non-integrability. Is the equation of motion in this case integrable, or is the equation of motion not integrable? What do we even mean? So I talked about this stuff by Flexner about the importance of basic science learning, basic learning of any kind. We talked about uh, nonlinear systems and wave equations and all kinds of effects that waves bring us. And we are kind of there right now. So we'll be there for a long time now, pretty much till the end of the semester. We talked about these rogue waves. By the way, rogue waves is a very current and exciting topic uh, for multiple reasons. Uh, from a practical point of view, uh, ships are, as you know very well at this current time, are incredibly important for us to survive. Because without ships, we don't get our fuel. Without fuel, we are cooked. So, by and large, ships are very important. But forget about fuel. I mean, almost anything you buy is not made locally, right? So we live in a very strange world where the toothpick that you might be buying came from China or Vietnam or someplace. You just it's quite amazing. But that's because ships are going around, and that's because the world kind of is supposed to run a certain way as far as we're concerned. So similarly, rogue waves are therefore, by definition, is equally important because the last thing you want is for your ship to go down. And this is what rogue waves can do. And so they're a major risk to shipping. And of course, shipping is done along the lines where rogue waves are relatively common, but still, it is there. So anyway, it's a very important topic for practical applications, real life stuff, as well as to the applied mathematics community, or to somebody who likes to do nonlinear system studies like me. And then I talked about, the history of evolution of these problems. We talked about, uh, the nature of the wave equation and the nonlinear equations that are nicely solvable. We haven't talked about solving any of them. And one of the ones that I hope to bring up today is solving at the very simplest level, very basic level, nothing fancy, the Korteweg-de Vries equation. And the Korteweg-de Vries equation keeps showing up in stuff that we will go through in the short run. And so the understanding of the Korteweg-de Vries equation is therefore rather good to have, I feel. By the way, this is just another thing. This is like a rogue wave. This is like a soliton in the ocean, as I pointed out last time. So even in the open ocean, you have soliton formation. I don't know how high this is. It may or may not be very high because I don't know the particulars of the picture that was taken. This is taken presumably from space, but not once it gets high, it becomes more dangerous. So we talked about the Toda chain and the solution of the Toda chain, right? This is something that we did last week. And this problem has thrown a sort of interesting twist to what we thought is presumably integrable and non-integrable. Really interesting twist. I told you that the Fermi-Pascal-Lamsingo problem, which we keep coming back to, is a non-integrable problem. This is what Fermi tried to do with Pascal-Lam and Singo, and I'll come back to that in detail today and this week at least. This is very similar to it because once you expand the exponential, you get a polynomial in R. And Fermi-Pascal-Lam potential has a quadratic term and a cubic term if it's the alpha model, and a quadratic term and a quartic term if it's the beta model. So it almost seems like the Fermi-Pascal-Lam should be a simpler version of the Toda problem because e to the minus br gets us all the powers. But this is where things go weird because this problem is solvable. This problem is integrable, whereas the other is not only not integrable, it is probably one of the stickiest challenges that the 20th century and the 21st century has seen in solving dynamics problems. Why? I have no clue, actually, because this is just solvable, the other is not. It is what it is. I mean, what are we going to make of it? So I showed you this thing, but it is pretty well understood. I mean, numerically and theoretically, you can see we have tried to take a soliton that is moving in a Toda chain from right to left. Initially, it's before 1400, it's at 1400, it's at 1300, it's at near 1100, is moving from right to left. And we can see that the numerical solution, which is here, and the theoretical solution, they're basically the same. There's a little bit of difference here for reasons that I don't know, but we are able to do it very accurately. Maybe the accuracy in this study wasn't all that much, or there may have been some boundary effects because that was a little bit hard to control. And this is the same data, but seen from the top, where you're seeing the energy propagating. So this is the soliton. This black line is the soliton. And then this is some oscillatory tails that are following the soliton. That typically happens if you have boundaries or if you have, depending upon the nature of the perturbation, this is the more general case than just a single solid forming. Now, let me focus a little bit more on the Toda problem, which I'm just reminding you, this part we have done. We have set up the equations of motion of the Toda problem. And this was the equation of motion. Then we set it up for the bond. If you remember that, we called it Rn. And then what we tried to do was we introduced a new variable, this eta n, which is e to the minus Rn minus 1. And then we rewrote the equation of motion in terms of 1 plus eta n, but log of 1 plus eta n. And then integrated it once to make it from a second order to a first order equation in log of 1 plus eta n. That brought up this form, and then eventually went back to another form which has the second order derivative. And then Toda had this very clever idea of seeing this through the lens of trig identities. You remember the discussion. We talked about the hyperbolic tangent function and its properties and identities. And from that, he could pretty much figure out that if beta is sinh square v, then the problem can be solved. So it was a brilliant discovery and solved this problem, ultimately leading to e to the minus Rn minus 1 having this Sech square form. Traveling function, so it's like a x minus vt kind of a function. The thing that I thought I would remind you, which is why I went through this quickly, is that the answer is actually, in this case, turns out to be an infinite series. But all of these are for Sech square functions. So the soliton that you see actually is going to be a Sech square. Now, the Sech square, by the way, is not for the displacement, although it looks like it. It's not really for the displacement function. The Sech square is more a description of the actual pulse, because Sech square looks like a Gaussian almost. And the displacement function actually looks more like a displacement function of one particle, not of a bond. Displacement function of one particle is more of a tangent function. So if you take a tangent function, or this function rather, then the tangent function, if you take a first derivative, that becomes a set square function, right? Basic trick. So this set square function really describes the displacement of a particle, or because this has been given a bond description, since a bond is not getting displaced, a bond is getting stretched and unstretched, squeezed and unsqueezed. For that reason, for the bond problem, you automatically get a set square form. But if you now want to come back to the particle picture, I just want to tell you that the particle's displacement is actually a tangent function. But the particle's velocity, because the particle kind of sits here, the wave comes along, it moves a little bit, and then slowly comes back to its original position. So particle's velocity or particle's kinetic energy would be a set square function. So this is how you want to visualize it. For the bond, it is just a stretch and a unstretch. But for the particle, it's going forward and then coming back. And for the displacement, it's just moving forward. So this is something we have done before. I hope you remember that part. But I thought I would add some material because this is a slightly different take on the same problem. So this is the chain. There are 100 particles in the chain connected by springs. The Hamiltonian satisfies the Toda chain problem. And then perturbations are initiated. This one is initiated in such a way that the wave moves towards the center. And this one is initiated in such a way that the wave moves towards the center also. So this is one wave that forms. And then because you are like squeezing a spring, you will necessarily be unsqueezing the other side of the spring. So you have one wave going this way and another wave going the other way. Same here. These are the boundary walls, and they gently reflect off the boundary walls. And then they come along and then they meet again here. And of course, as you move along, it continues to meet repeatedly. Now, in one case, this is for fixed boundary condition. In the other case, it is for periodic boundary condition. Point being that whether you have fixed boundary condition or periodic boundary condition, the detail may be slightly different, but the problem itself doesn't behave super differently, meaning you don't get non-integrability or this and that. Once a problem is seen to be integrable, then the problem is integrable, regardless of boundary conditions, regardless of initial conditions, the problem is integrable. That said, the initial conditions can change the flavor of the solution quite a bit. And this is exactly the point I want to try and convey today. This is not something that textbooks cover, but this is something that turns out to be a very interesting thing to notice. So you see, if you look at it carefully, although these solitrons collided, these solitrons didn't affect each other very badly. The tails kind of led to some interesting pattern, but the tails didn't get distorted or damaged. If you let it go forward, it'll essentially retain its form. It's just that you are seeing a lot of interference of things that are moving forward, but it's not like the interference is driving the vibrations of these particles to a quote unquote chaotic site. It's not that. That is the point I want you to take away from this picture. And to be brutally honest with you, it took me a long time to get this point because I have spent hours observing these little wiggles here and here to make sure that these guys are going through each other without really messing each other up to the point that they would become chaotic. And my conclusion for a long time was I couldn't tell, but now I sort of can tell that they look almost the same. Slight differences will come because one has fixed end walls, one has periodic end walls. But now what happens if you let this movie roll on by? What happens to our system? Now this system is not exactly the same, by the way, as this system, where two perturbations were given at the same time at t equal to 0 at one end of the chain. Okay. This was started by one perturbation, a perturbation of velocity of magnitude 0.05 in system units at mass 51 in the total chain with fixed boundary condition. I also have a picture for periodic boundary condition, but I may not have thrown it in here. It is different. It's not exactly the same. Now, if you look at it without without being biased or anything, what do we see? Well, we see some really interesting stuff. We see these long, long lines. And these long straight lines almost definitely means the propagation of solitons because they always move with fixed velocity. So whether they're going in one direction or another, this way or that way, it's really a collection of straight lines. You also see some rather high peaks. These rather high peaks would naturally come when all these many, many solitons that have now formed, they collide. And then you have this background grayscale. And the grayscale, if you look at it, it's hard to see in great detail, but much of the grayscale are those tiny, tiny oscillations that had formed at the tail end of the soliton. So in other words, what I'm saying is the grayscale is nothing but formed out of all these little guys here. The not so grayscale, somewhat intermediate sized peaks are also coming from some of these things. It depends upon where they're colliding. And then the more bigger peaks, of course, are coming from the largest of these pulses. So it is not impossible then, without theorizing that something very bad has happened or things are going completely chaotic and so on, to stare at this picture and say, oh, it is possible, I guess, to have a situation like this. By the way, all the masses are exactly equal. There is no impurity. That's an important point because impurities can break translation symmetry. And by breaking translation symmetry, can introduce a plethora of important dynamical effects and breaking, integrability also. Yeah, Vivek.
Yeah, if we can I draw?
You can
I
draw.
don't.
I don't know if you can draw. There is a whiteboard. I've never used it. Let's see. I don't know if I can turn on the whiteboard.
Yeah, I can draw. I can draw. No,
Okay.
no, I can't.
You can draw on a piece of paper and show me.
Okay.
This is not yet. I'm going to come back.
So yeah, if you
Hmm.
look at
Not letting me go back. 1 second. It's locked up the bloody screen for me. Why? Okay, yeah, tell me. Yeah.
Can you see this square?
No, it's too little. Let me see. Let me see. Hang on. I can see, yeah.
So I can notice the two lines in this graph. If you look at that 99600 and going it diagonally to 9 to the other side.
Okay, hang on. This thing is complicated to manage, I guess. Line here, 9600.
Yeah, and then go it diagonally. So sideways
Yeah,
to,
yeah, yeah, yeah. It is this one. Yes.
yeah, that
Something
one, that
happens
one.
here and then again
Yeah.
yeah.
And
So
similarly line at 9900.
yeah, so these are probably the solitons that are coming together.
Okay.
But there is the thing that is not happening is that these solitons are not creating new smaller solitons, but the smaller waves that we're following, which are a mix of solitons and spring-like vibrations, because that's what the potential is, right? They are interacting. It's not that they are not interacting. So, and those interactions, the wave parts, we know will give you, all kinds of effects, right? When two harmonic waves meet, you can have these beating patterns, you can have all these patterns. So all those things are present because the harmonic behavior is actually sitting inside. So this is the reason why, at first glance, it can look quite chaotic. And that's what I thought it is. But then when I began to educate myself more and more, it became a question as to whether it is to be interpreted as chaotic or it is to be interpreted as just an effect of the interactions between the harmonic waves, the nonlinear waves, and the mix of the two. Now, existing mathematical progress points to the mix of the two, and it's just a non-chaotic thing. So that is the interpretation I'm going by. But it gets worse. Kinetic energy versus space versus time. It's really quite crazy, I think. And here you see that there are waves that are rather large. And in fact, this would be what I would call a rogue fluctuation, because uh, this kind of a wave sucks up a significant part of the system's energy. And they come after uh, usually after many thousands or tens of thousands of time steps of the run. They don't come very often. In fact, it's the dark blue that is more common, in this case in the energy scale. But this yellow is definitely not very common. So, the, is this not chaotic? By every account, it seems chaotic. By the way, this is a perturbation that is different from the previous perturbation. In the previous perturbation, it was a single velocity perturbation. Here, every particle has been given a random velocity, just to see how wild it can get. We did that. And when we did that, this is something that we got. In fact, we haven't published this. I'm going to submit this paper soon. Um, I'm actually quite worried about submitting this paper because I'll get a lot of pushback. Because people will say, "What have you done?" The answer is, this is what the system gave us. And I know that our energy conservation is essentially perfect in the simulation. So I know that the calculation is not wrong, but this is what we get. So the level of interference that happens is dense, is all I can say. It is very, very dense. So you read this. I'm going to be back. I need to use the restroom. Um, let me.
You are muted.
Okay.
Can you hear me?
Yes.
Okay. So anyway, so I'm just trying to point out a few things here. We have discussed the solution to the problem with no impurities. That's the only case that can be solved. The solution that we discussed was the system was essentially infinite. So boundary effects that can mess things up badly is not in that solution. So that was the Toda solution that I talked about, which was this one here. This one, the one we just discussed. In this solution, boundary effects are not there. Okay. Now, what happens is in these two solutions, in these three pictures, boundary effects are there because one is a fixed boundary, one is a periodic boundary. So you can see that things are very complex with boundaries. Now, regardless of that, this is fixed boundary. Regardless of that, regardless of initial conditions, the underlying fact is that the systems remain integrable. The solutions change, but the system remains integrable, which means that it can, in principle, be solved in closed form. That's what typically it implies. Now, people have solved both these problems, the one with fixed boundaries and the one with periodic boundaries. These solutions have led to literally marked improvements in our understanding of how complex this problem is. If you look at the papers, the mathematical analysis of the problem in papers, where boundary conditions like fixed or periodic boundary conditions are incorporated, honestly, they are bears. I mean, it would take me months to work through them if I were entirely doing it on my own, given how busy I keep. It'll literally take me a month. It's that bad compared to what I gave you, which is one reason why I'm not taking you there. But these papers exist. These papers led to marked progresses in the understanding of these systems, and they have become new techniques and so on. So boundary conditions, therefore, have played havoc in our understanding of the Toda problem. Toda, by the way, himself didn't solve these periodic and fixed boundary conditions. They were solved by others like McLaughlin and all these amazing people that came along. Flashka, you'll hear these names. They're like household names. They are the ones who created these solutions. It is agreed upon that the Toda problem with a single impurity can drive the system to a chaotic state, meaning it can go to equilibrium. That's what this means. Chaotic state means that the motion can become very disordered, and eventually the system reaches equilibrium phase where the energy is equipartitioned and so on. Memory of the initial condition is gone and all that. So it is agreed upon that the Toda problem with a single impurity can drive the system to a chaotic state. In other words, the eventual equilibrium state. However, the single impurity Toda problem itself has not been that well explored. It has been well explored. In fact, if you were to pick up or do a search, you will find that the last 15 years also has many physical review papers on the impurity, single impurity, or two impurity, or multiple impurity Toda problem. You remember seeing when I presented to you the more general harmonic oscillator chain problem that Professor Yu had worked on with M1 and M2 and two or three mass possibilities, how complex those got. How complex those got, we couldn't dig into because they were just too complex for us to dig into. You remember that? That was the Professor Yu's solution. I'd show you. I'm talking about the stuff that we here. You remember all these solutions that we had worked on a long time back? We worked all these deltas. I showed you alternating mass cases. I showed you how the relaxation function would begin to vary. Uh, all these cases incorporated just two masses, M1 and M2. But this is a linear problem. This is simple harmonic motion. Remember how bad they were? I'm talking about the same problem now in the nonlinear context. Okay, so nonlinear context, when you have similar problems, things you basically discover new physics, new mathematics. So this is one of the things that I wanted to bring up for the simple reason that progress happens in these fields almost always in small steps. And in modern times, in small steps taken by many people who are independent workers. And it is the summative input of the independent works of many people from across the world that shape our current understanding. Of course, that itself is quite chaotic to sort of go through and absorb. But I'm trying to give you this absorbed information, insight that impurity, soda problems with impurities, it's a classic problem because soda is solvable. With impurity, it becomes unsolvable. So you cross over from a solvable to an unsolvable version of the problem. Solvable analytically, unsolvable analytically is what we mean. And then tells you how the system evolves in late times. Does it have a strong engineering application? I don't think so. But does it form the building block of important applications of nonlinear physics? I think so, very much so, because most real systems are not pristine. Most real systems have impurities and all these differences built in. And so best we can do is break them up into more manageable problems first, do the manageable versions, and from that we construct our pyramid to come back and see where we are. So here I say approximate a non-integrable system with an integrable system, okay or no? I don't think that any of us can give you a very good answer to this question. In fact, this is a question I have often asked my very brilliant applied mathematics colleagues who are close friends. And there is a big distribution of thoughts. I personally don't think approximating a non-integrable system by an integrating system for studying the long-time dynamics, I personally don't think it's very useful because I think they're different. It's useful in the sense that it's important to understand the differences. And I think most applied mathematicians who prefer a more structured theoretical way of studying these problems, they have little choice but to approach it through the integrable problem channels and to see where it is non-integrable and what does non-integrability mean. The answers to even that question remain relatively, scantily understood. I wouldn't say that they're extremely well understood. They're somewhat understood. And in that vein, let me now return to the Fermi-Pastor problem, which is the third time I'm returning, I think, in this class, because you can't get away from it. It's like a magnet; it draws you back every time. And I want to bring up something which is a little bit more introspection oriented. I don't know how much you know about Fermi. Most of us didn't know much about Fermi. Fermi passed away many years ago in 1954. But of course, Fermi had an almost godlike importance in the world of physics because he simply was one of those guys who was immeasurably capable. we of course hear a lot more about Feynman because Feynman was much more recent. Feynman, lived until 1989. Feynman gave those great lectures in Caltech, which became the Feynman lectures. He wrote many books, and Feynman lived until 69. Fermi died at 54 or 53, 54, I think, maybe 53. But so he had a much shorter life. And if you look at what Fermi accomplished, um, it is my personal belief, my personal thinking that Feynman looks almost like a dwarf, if I may say so, compared to Fermi. So before I take you to Fermi, let me remind you that you have learned enough now to observe that if you take this alpha FPU problem, FPUT problem, the alpha term, this is an equation of motion. Quadratic term in equation of motion means a cubic term in the potential. So alpha FPUT problem, if you study it in the long wavelength limit, which means that the lattice spacings become, particles come close to each other, lattice spacings go to zero, system size goes to infinity, then it basically lends itself to a Korteweg-de Vries problem. The Korteweg-de Vries problem has been analytically solved. It becomes a Korteweg-de Vries problem in a limit. It's not exact. And I will show you one of the ways of solving the Korteweg-de Vries problem. I won't get into super detail, but just the easier way I'll show you. The Korteweg-de Vries soliton also has the same form. Most solitons have this Sech square form coming in. So 3v Sech square root of v over 2x minus vt. This is some kind of a, this kind of a function, which can be a bond stretch going down. This can be in this case, there's no bond. It can be a piece of the medium going up and down or going forward and backward like that. It's more forward and backward. It's one-dimensional. So anyway, so the point is that Fermi-Pastor-Ulam problem, for the alpha problem, for this problem, one can approximate that with the Korteweg-de Vries problem. And so what does it tell us? Why is it a big deal? But it's a big deal because this Fermi-Pastor-Ulam problem, when it was done, it pretty much left everybody who cared to understand these systems from the time frame of 1955 until 1965 in confusion. And I want you to understand why this confusion came. Now, in this confusion, there was a little bit of light all of a sudden. And the light that came along came from the Zabusky and Kruskal paper of 1965. And the Zabusky and Kruskal paper of 1965 showed people that the Fermi-Pastor-Ulam-Singo problem likely has this soliton sitting in there. But that is not something that Fermi-Pastor-Ulam and Singo noticed. In fact, they were not even in that ballpark of a soliton. So this was, this was a complete side game, a sideshow that merged with the Fermi-Pastor-Ulam problem in its own way. So why was this problem creating so much confusion? Remember the words I said, that Fermi had an almost godlike importance in physics. So just to go over Fermi's CV a little bit. So Fermi introduced what we know as Fermi statistics, and that came in 1926. Fermi was 1901 born. He was 25 years old. He discovered statistical laws governing particles now known as fermions. First thing. Second, Fermi introduced the beta decay theory, developed the theory of beta decay in 1934, incorporating the neutrino. Two incredibly important advances just came from one brain. Third, neutron bombardment demonstrated that slow neutrons can induce radioactivity and nuclear transformation in elements. Basically, how elements transmute. Also goes back to Fermi. The first nuclear reactor, which we take for granted. We're trying to destroy the ones in Iran, for example. On December 2, 1942, he led the team that achieved the first self-sustaining, controlled nuclear chain reaction at the University of Chicago. Fermi was a big player in the Manhattan Project during World War II. His work led up to the first bomb, not something that any of these physicists wanted to do, but that's how things happened. Fermi used to be a professor at La Sapienza at the University of Rome. La Sapienza, University of Rome. He left. He left because he married this Jewish woman, Laura Capone. This is a picture from his wedding. This is Laura. This is Fermi. This is his father-in-law, who was an admiral. Let me enlarge it a little bit. It's kind of small. I was quite thrilled to find it in the archives of Chicago, actually. So here you can see Fermi. Here you can see Laura Capone. And this was in 1928. That was the year. And this is Fermi much later, presumably in his Chicago office, I would say. But Fermi came to the US in 1938, in part because he was getting increasingly concerned about the safety of his wife, who was Jewish. So he basically moved to the US at that time. And I believe that was also the year he got the Nobel Prize. So Fermi first became a professor at Columbia University, and later he moved to University of Chicago. Element 100, which is fermium, is named after him. Fermilab is named after him, of course. And he died very young, as you can see. He died on 28 November 1954 at the age of 53. So this is a brief CV of the kind of man Fermi was. Fermi was an experimentalist of great repute. He was a theoretician of great repute. He got things right. Okay? Fermi got things right. And Fermi got major different things right all across physics. So why is it that Fermi had so much trouble with this problem that he wanted to address about equipartitioning of energy, about modes being dispersing and mixing, that we had assumed in celestial mechanics from the early 1800s? Why is it that Fermi decided to go back to this problem? And he was left completely flummoxed by the results that he got. He just didn't know what to make of it. And he made a comment. I'll come to that comment. But this is why the history is very important, because the history helps you put the problems in the context. Physical review papers don't, but the history does. So this paper is particularly good about history, and it's available actually. You can Google it and get it down. The Fermi-Pasta-Ulam problem, paradox turns discovery. Paradox because Fermi couldn't explain. Pasta and Ulam also couldn't explain. By the way, Pasta and Ulam were no little people. John Pasta and Stanislav Ulam were very, very celebrated people at the time. And Stanislav Ulam was a world-class mathematician. He knew his stuff. It was widely regarded. It was an all-star team, and the all-star team couldn't do it, couldn't explain the problem. So this gentleman, who I have listened to as a graduate student, he passed away in '95. Joe Ford. Joe Ford was a Regents Professor of Physics at Georgia Tech. So when I was a PhD student at University of Georgia, Joe Ford was invited to give a special talk, special lecture, and he had come. And he gave what was one of the nicest lectures I've ever heard in my life. He was one fantastic speaker, a very colorful man, and he had his own take on physics and on this problem, in which he remained in authority all his life. So he says here, and this pedagogical review is written as a personal retrospective which seeks to place the celebrated Fermi-Pastor-Ulam paradox into historical perspective. After stating the Fermi-Pastor-Ulam results, we treat the questions it raises as a pedagogical skeleton upon which to drape and motivate the evolving story of nonlinear dynamics and chaos itself. Because the whole business of doing nonlinear dynamics and chaos goes back to this problem. That's why we keep coming back to this problem. And we will be coming back until the end. This review is thus but another retelling of that story by one intimately involved in its unfolding. Because this is what he used to do. He was a specialist in this problem. This is done without apology for 2 reasons. First, if my colleagues have taught me anything, it is that an audience of experts will seldom pay greater attention than when, with some high modicum of grace and polish, they are told things they know perfectly well already. Second, if generations of students have taught me anything, it is that few things fascinate them more than a scientific mystery. And the Fermi-Pastor-Ulam paradox is a crackerjack mystery. And so readers, especially graduate students, curious about nonlinear dynamics and chaos, are now invited to sit back, loosen their belts and minds, and prepare for fact that sometimes reads like fantasy. That is the abstract of this paper. And man, this is a good paper to read. So I'll email it to you, guys. It's a fantastic paper. Fairly long, about 40, 45 pages, but it's super duper, in my opinion. And Joe Ford was a better speaker than anybody else I've ever come across. And I've come across some really good ones. One of them was Willie Fowler, who won the Nobel Prize for nucleosynthesis and determining the age of the universe. The age of the universe was found from the abundances of the heavier elements in the sky. So observationally, we figured out the heavier elements in the sky, and from that, it was possible to calculate how long it must have taken for those guys to form, starting from a Big Bang. And if you do that calculation, which is what Fowler did, Fowler came to the conclusion that the universe is between 11 and 13 billion years old from nucleosynthesis-based studies. And this is what led him to get the 1985, I think, Nobel Prize with Chandrasekhar. So he was one hell of a speaker. I mean, he could really drive a crowd pretty much crazy in the way he spoke and presented. Even a dinner crowd went crazy with his lecture on nucleosynthesis back in 1989. Anyway, so Ford was like that. So let me just take you now a little bit to the physics. I'm past time, so I'll come back to this on Thursday. But he starts off detailing how Fermi-Pastor-Ulam and Singo took this problem in detail. So after much back and forth, FPU decided to numerically integrate the weakly nonlinear fixed end one-dimensional chain of n-1 moving mass points having this form of the Hamiltonian. Q0 and Q of n were by definition 0. So that means the endpoints were fixed. Qk and Pk are the coordinate and momentum for the kth particle, where alpha is a small nonlinear coupling parameter. And where the particle mass m and harmonic spring constant k have been eliminated by a standard canonical transformation and a change of time scale. Concurrently, FPU also considered chains of particles whose Hamiltonians had quartic or broken linear couplings, as well as cubic nonlinearity explicitly written above. So he just lays down the problem, and then he goes to lay down the approach that was taken at the time. Because the weak nonlinear terms in the FPU oscillator seems primarily FPU oscillator systems primarily serve only to cause energy sharing between the perturbed harmonic normal modes, it becomes natural to present the final results in terms of normal mode coordinates AI. So this was the angle that they took. They said, well, the nonlinearity is supposed to mix the normal modes. If I have a system with normal mode vibrations, a harmonic oscillator chain, we might as well start with normal modes and see how these modes are mixing. So they take the normal modes and they stick the normal modes back in the Hamiltonian, so they get this Hamiltonian. And this Hamiltonian is written in terms of the normal mode frequencies omega k right here. Okay. So now you understand why they took the angle they took about starting with normal modes. And then you go to the problem itself. I kind of write it out. And you stick in the x and x dot and all that. And from that, you work through the problem and simulate it. So you've stuck in the normal modes in the problem at t equal to 0. And then you expect the modes to start to mix. This is basically the story. And let me stop here because I know that, Tony, you have to do work, right? At 4 or something? Okay. So let me stop here because it's about 3:21. What I'm going to do is I'm going to come back Thursday and take you back down into the sort of backside, if you will, of the Fermi-Pascal-Lamb-Singh problem. And to focus on this mode mixing business, how they started, what kind of mode mixing they observed, and why Fermi was so puzzled by it. Because it is a problem that has had some progress in terms of why Fermi, Pascal-Ulam, and Singh had so much difficulty. So I want you to be able to see the progress that has happened. For example, there was a conjecture made in 1985, and that conjecture in 2015, 30 years later, has been shown to not be quite right. So there has been progress in coming towards the point that what Fermi, Pascal-Ulam, and Singh expected actually does happen, but it doesn't happen as expected. Okay? And the papers that have been able to study how it happens are a long time coming because there are very, very few studies that actually have been able to make it go the way in such a way that one can see what is ultimately happening. Okay, the way the progress has been made is quite tricky to follow. So I don't want to spend too much time, but I want you to at least see why this is such a big deal and what ramifications, more importantly, it has in how we understand nonlinear phenomena today and why the problems are the problems that you see people do. So let me stop there for now because I want to spend a bit of time on this Ford's take. Ford had a very interesting and I think rather important take on this problem. So it is going to be good for you guys to be able to see that a little bit. All right, let me stop sharing, stop recording.